All right, anybody have any homework questions you want me to go over?
Problem all of them.
Okay.
Throw it in the garbage.
Was it really like that?
No, I haven't even done it.
Oh,
I haven't
okay.
even looked at it yet.
Okay.
Or the one from Wednesday.
Not course notes.
Yeah, 2 was the craziest.
Okay.
Really, I started to kind of get it, and the first one actually made sense.
This was on, what are we on?
One.
Second law. Entropy, part 1. Okay. Okay, so you got this piston cylinder thing and air in it, and it undergoes a power cycle. Carnot cycle is just a type of power cycle. I guess. Okay, so it tells you it's isothermal. Damn it. One thing that you'd probably have to know here, and so if you didn't know this, I apologize, is that a Carnot power cycle is an idealized cycle that's internally reversible. In fact, it's not even internally reversible, it's a fully reversible cycle. And so we're probably going to have to use that fact. So, what do we know since it's reversible? Well, we know that the efficiency of this cycle is the ideal efficiency. Remember that? So any reversible power cycle has the same efficiency given the same 2 thermal reservoirs. And you can calculate this as 1 minus the temperature at the cold reservoir divided by the temperature at the hot reservoir. Okay, so we're likely going to use that. Isothermal expansion and compression. So it just tells you the 2 reservoirs, and it tells you the 2 pressures. Okay, so the isothermal expansion. So this happens at the high temperature reservoir, and so what can we figure out? So we can figure out so the pressures at the beginning and end of the isothermal expansion. So this thing, how much do we have to know about this Carnot cycle? Well, let's do the easy one first. So the thermal efficiency is just going to be, okay, well, that one's just plugging in. That just requires knowing that this is reversible, which I didn't tell you. So this is 1 minus, this is already given in Kelvin. So 350 over 1400. So 0.75. The heat transfer for each of these processes, we should be able to do that because we know that, again, this is reversible. We should be able to say that, well, we know that the change in entropy is equal to the integral of, the amount of heat that's transferred divided by the temperature plus the produced entropy. And so for the isothermal expansion,
So does that sigma have to be 0 since it's the Carnot?
yes, that's right. That's right. And so so this is 0 because it's reversible. And so we're going to be able to, if we can calculate that change in entropy, since we know the temperature, we can just figure out the heat transfer. We are going to assume, so we're assuming this is an ideal gas. It said that somewhere, right? Didn't it? Yeah, assuming ideal gas model. Okay, so let's figure this out. And let's say I'm thinking that, so there's an isothermal expansion and an isothermal compression. There's 2 other stages. I'm thinking, and obviously, like, you don't know that. I don't even remember that. But I'm thinking that this is saying also that we're going to start the isothermal expansion at the 500 kilopascals. So that's going to be our P1, and our P2 is going to be 100.
So that's just the answer to A, because it's a cycle.
Oh,
right? Is that?
I guess that's my answer to A, but I don't know if that's true or not.
It kind of makes sense, though. I mean,
yeah, I mean, I just have to look up what the other stages are. It's like I think it's these 2 isothermal things, and then there's 2 I think 2 adiabatic things where there's no heat transfer. I don't remember. But so what we have to do is come up with, so I'm assuming these pressures so that we can come up with what we need to calculate that change in entropy. And so, and does it say the mass? No. So the change in entropy is equal to the mass times the change in specific entropy. And that is equal to, we did this last time, so this is Cp times the natural log of temperature 2 over temperature 1 minus R times the natural log of P2 over P1. And so the change in specific entropy is equal to, we were given this Cp, so 1.005 times 10 to the third divided by the mass times the natural log of this is isothermal. Okay, so isothermal means the temperatures stay constant during this process, so that first term goes to 0. So all we have left is this second term, and that's R divided by the mass times the natural log of, now here's where I'm making that assumption about the pressures. So 100 over 500, and this is negative. And so R is, we've been using 287. We still don't know the frickin' mass. The natural log of 0.2. So this is negative 1.61. And so this is 461.91 divided by m. Okay, so that is the change in entropy, is specific entropy. And so the change in extensive entropy is this times m. So this is just equal to 461.91. And that's equal to the heat transfer divided by the temperature, which was 1400. And so the heat transfer is,
Did you say it's divided by the change in temperature?
no, I'm just using this now.
Oh, in that state.
Yes, I mean, it's just going all the way around the boundary. So this is the temperature at the boundary the whole way. You know, this here is our, this is our integral delta Q over T. And so Q is equal to 646, 676 joules. And then the work, well, the first law says the change in internal energy is equal to heat minus work. For an ideal gas, we know that the change in U is equal to CV times the change in temperature. And CV is, what were we given, CP? CV is CP minus R. So this is a constant.
Isn't delta T 0?
Yep. And so this all goes away. And so we know that there's no change in internal energy. And so now we have that 0 is equal to Q minus W. And so W is also equal to 646, 676. And then we'll do the same thing for the,
What was part C? The thermal efficiency.
yeah, we did that first. That was the one where you just had to recognize that it's reversible. For part B, we're also supposed to do this for the isothermal compression, but it's just doing the, it's just using the opposite values of things and the temperature at the compression. So for the isothermal compression, again, we know that delta S is equal to the integral of delta Q over T plus the entropy produced. This is 0 because it's reversible. Delta little s is equal to Cp times the natural log of T2 over T1 minus R times the natural log of P2 over P1. This goes away because it's isothermal. What did I, well, okay, this, I made a mistake here with these M, so we are still gonna have to deal with this M. Because this is 461M. And so Q is equal to this times M. But now you can go delta S is equal to 1005. We don't even need that. So minus 287 times the natural log. The pressures are reversed, so this is 500 over 100. And so this time you get positive 1.61. So negative 462.07. 461.91. I'll use the old one. Okay, so we got negative this time. And so delta big S is equal to negative 461.91 M. And that is equal to the heat transfer divided by the temperature. So that's Q over, this time the temperature was 350 Kelvin. And so Q is equal to about negative 161.725 M. And by the same reasoning, work is equal to negative 161.725 M. And this W should have an M here too.
And is there a way to figure out the mass?
Not that I see. Let's think.
Well, we don't need it, right? We just cancel out.
It didn't cancel out. When I did that before, I was wrong. Because, so I just set up an equation that I set the wrong thing equal to the wrong thing, and that made it look like it canceled out. But what we really know for an ideal gas with a change in entropy is the specific entropy stuff. And so I think, I really don't think there's a way. I think you probably have to do it in terms of the mass.
Can live with that.
If it gave you a volume or something, then we could use the ideal gas law to calculate the mass, but I don't think we can. Some of these answers you just have to give in terms of masses. I mean, that's just something we see sometimes.
For the quantity, like P2 over P1 in the Lund, is that interchangeable with like volume? Other stuff?
This stuff here, the natural log of P2 over P1, if you have the volume instead, we have a different equation that works. So remember, we have these two equations. Delta S is equal to CV times the natural log of T2 over T1 plus R times the natural log of specific volume 2 over 1. And we have the equivalent statement, Cp times the natural log of T2 over T1 minus R times the natural log of P2 over P1. And the negative and positive come because those, the volumes and pressures are inversely related to each other. I left you guys hanging out to dry on that one. I'm sorry. I mean, you have to know something about the Carnot power cycle, which I don't even remember. I just assumed that
It
this.
mentioned it on the key. Like,
Oh, it did?
yeah.
Oh, well, that was good. On the
What
key.
hell?
That's a little late, but
Yeah.
better late than never. But it all hinges around knowing that it's a reversible cycle. But what you should take away from this is not that I gave you a problem unfairly. It's that the relationships between things that you get when you have a reversible cycle or a reversible process. Okay, like because this was a reversible cycle, we could calculate the efficiency just from the temperatures. And because this is a reversible power cycle, we have a relationship between the change in entropy and this integral of delta heat over temperature. Okay, so look for that. I mean, that's sort of a class of questions that that can be asked, and in a few different ways. And so be ready for that. Like if you see, really as soon as you see that you're dealing with a reversible process, that should pop into your head. Like maybe first, okay, if it's a cycle, a power cycle or whatever, I can calculate. I know some extra stuff about the efficiency, but mainly if it's reversible, this relationship between the change in entropy and the heat divided by the temperature. Okay. That was hard. Any other homework questions? Good job not doing it. That was the best choice of all. No, but I say that, but remember the thought process here. If the question was cleaned up a bit, that would be a very reasonable question.
I mean, I did it now.
Okay, yeah.
It's about equally messy to yours.
Yeah.
Nice work.
Yeah. Yeah, any other homework questions you want me to do? Okay, there's another thing that we can do with ideal gases. So this is going on to the next stuff. This is isentropic processes for ideal gases. Isentropic means that the entropy is constant as this thing happens. So entropy is constant during the process. And what that requires, you can think of this as two things. First, there's no heat transfer into or out of your system. And second, it's internally reversible. And remember, internally reversible just means that inside the system, there are no irreversibilities. None of those 7 things that I gave you as causes of irreversibility.
So is this possible?
It's not possible, but it's often a reasonable approximation of real stuff that happens. Just like a skateboard can't roll down a ramp without friction, but often you can get good information from assuming there's no friction. Okay, so what do we know in that case? Well, it actually comes from these. Remember, this is for an ideal gas. And so if there's no change in entropy, you can set the two right sides equal to 0. So then for an ideal gas, You have that 0 is equal to Cp times the natural log of T2 over T1 minus R times the natural log of P2 over P1. And 0 is equal to Cv times the natural log of T2 over T1 plus R times the natural log of little v2 over little v1. And if the change in temperature is small, you can use these directly. Because then you can assume Cv or Cp are constant. But what we did before is we also had values we could look up in an ideal gas table for that allowed us to give a more accurate calculation. And we're going to do the same thing here. So for bigger changes in temperature, or for more accuracy, you can put this equation into a form. So let's see, which one are we using? So we're going to use the Cp one. So we'll go Cp times the natural log of T2 over T1 is equal to R times the natural log of P2 over P1. And then we'll get this side, oh no, the other side alone. So we're going to go natural log of P2 over P1 is equal to Cp over R times the natural log of T2 over T1. Then we'll raise each side, e to the power of each of these two sides of this equation. So we have e to the natural log of P2 over P1 is equal to e to the power of Cp over R times the natural log of T2 over T1. And this is just equal to, so e to any natural log is just equal to the argument of the natural log. So we have P2 over P1 is equal to e to the power of and okay, I'm not going to go through all this algebra, but so we have e to the power of S0. Remember the S0 that we had from the table before at T2 divided by R divided by e to the power of S0 at temperature 1 divided by R. And these two, the numerator and denominator here, are what you can look up in the table. This is the P sub R at T2. And this is the P sub R at T1. And these are in ideal gas tables. On tests and stuff, I mean, I'm a lot more likely to do it for a small temperature change and let you just do this calculation than make you go look for values or whatever. And since we have two of these, so everything starts from this change in specific entropy, and we have two of these equations. So you might imagine that there's this way of calculating a change in pressures. Maybe there's also a way in calculating, not a change, but a ratio of pressures. Maybe there's also a way like this of calculating a ratio of specific volumes. And there is. So just starting with the other equation, you can get V2 over V1 is equal to VR at T2 divided by VR at T1. And again, these are just given in the ideal gas table for a certain temperature.
Oh, that's P sub R.
Yes, not times R. Yeah.
Is that's pressure relative? Is that what that R is?
Yeah, that's right. Yeah. But this is what it really means. But
Got it.
so the answer to this is if you can reasonably make these two assumptions about an ideal gas, that there's no heat transfer during the process, and that this process doesn't have any major inefficiencies inside the system, then you can calculate these relationships between final temperatures and final pressures, or final temperatures and final volumes. Okay, I want to do one example. So this is something we used to do for a Physics 1 lab. So we're going to say there's air at 22 degrees Celsius and a pressure, 1 atmosphere of pressure. And we put it into a syringe. And then we compress it to half of its original volume. And we want to know what's the final pressure assuming first that this process is isothermal. So that's saying that the temperature stays constant. And second, assuming isentropic. Okay, so if we assume that this is isothermal, we have we're going to treat this as an ideal gas. So we have P1 V1 equals R times T1. And I'll just write this, well, and then in the second state, since it's isothermal, the temperature we're assuming isn't changing. We have P2 V2 is equal to R, also T1. And so then you just have P1 V1 is equal to P2 V2. And so P1 V1 is equal to P2 times V2. We can write this as, we've cut the volume in half. So we can write this as 0.5 V1. And so cancel the V1s, and you get that P2 is just equal to 2 P1. Okay, so if you cut the volume in half, you just double the pressure, right? So P2 is just equal to 2.02 times 10 to the 5th pascals. Okay, so this is what we did in a physics 1 lab, okay? But it never came out, the answers never came out very good.
You're saying when you actually measured it.
That's right, like we had it set up to, it was kind of in the right ballpark, but, so this was a physics 1 lab. But, the results never came out quite right.
So if you did it and then waited a while for the temperature actually to...
Yeah, so...
Would it be better?
I would guess that that's true. And so the issue was that, this syringe is plastic, and heat just doesn't transfer through that plastic very well, And so what if instead of assuming that this temperature stays constant, we assume that no heat transfers across the boundary of the syringe? Okay, we assume instead of assuming that that the temperature stays room temperature, we just assume that this syringe is insulated and calculate using an isentropic approximation what, so what, part B? What we would get for the pressure. And you get better, closer results doing this. And so the way that we would do this, we're going to assume that this is a small temperature change. Small enough that we can use the equations and not use the ideal gas tables. So okay, we have these two equations. We have 0 is equal to CV times the natural log of T2 over T1 plus R natural log of V2 over V1. And so this says that the natural log of T2 over T1 is equal to negative R over CV times the natural log of V2 over V1. And we'll use the other equation that says 0 is equal to Cp times the natural log of T2 over T1 plus R times the natural log, minus R times the natural log of P2 over P1 this time. And I'll rearrange that one also for natural log of T2 over T1. So this is now equal to positive R over CV times the natural log of P2 over P1. And now I'll set those two things equal. So we have R over CV times the natural log of P2 over P1 is equal to negative R over CP times the natural log of V2 over V1. And so multiply CV to both sides, and you get natural log of P2 over P1 is equal to negative CV over CP times the natural log of V2 over V1. Now take e to the power of both sides. That gives you P2 over P1 on the left, and e to the power of negative CV over CP times the natural log of V2 over V1. And what you get this time, where is that thing? Is that P2 is equal to about 2.66 times 10 to the 5th pascals. So the fact that that temperature is not staying the same has the effect of raising the pressure in there more than you would expect by assuming that it's isothermal. Any questions about that?
Are we gonna have, so is this more of like a derivation, or is this something that we might have to actually?
Okay, yes. You don't have to, I gave you the derivation just so you know where it comes from. It just comes from these same two equations for delta S that we've been using for ideal gases. Any entropy thing that mentions ideal gases or air, assume you're going to use these equations, okay? But the rest of it is just saying, okay, we have this idea of an isentropic process is a useful thing in a lot of cases. There are processes that meet that assumption pretty well. And in that case, you have equations you can use to calculate relationships between temperature and pressure, temperature and volume, or volume and pressure. Okay, and other than that, I mean, I guess this part of the derivation you should get comfortable with. It's really just manipulating logs and exponentials. You don't need to worry about the derivation of the any of the where did I put those? You don't have to worry about the derivations of like these relationships. Those you just look the values up in the table. You don't have to worry about the, I mean, these derivations are kind of immediate as soon as you assume that there's no change in entropy.
Mhm.
But just think of that as one more thing in your toolbox. Like if you can assume isentropic process and ideal gases, then you have all these new relationships you can use. Okay, that's all.